Hi, I'm Lindsay from StatsMedic, and in this lesson today, we are talking again about chi-squared goodness of fit tests. We're taking what we learned yesterday, where we were introduced to chi-squared, and making it a bit more formal today to run a full significance test. So we have 3 learning targets. The first is to state and check conditions, and those conditions are going to be random, 10%, and large counts. Then we're going to perform a full chi-squared goodness of fit test. And then we're going to conduct a follow-up analysis, and we do this when the results of a chi-square test are statistically significant. So let's go ahead and look at the note page. So we're using the same context as yesterday. We're looking again at this claim distribution of M&M color and trying to decide if we think that's true. So I've already gone ahead and filled in all of the observed values, expected values, and the test statistic that we found yesterday. So take a moment and copy those values down, and then when you're done with that, I'd like you to complete the rest of the front page. So questions 2 through 5 on the front. Take a few minutes, go ahead and pause the video and complete these questions, and when you're done, push play and we'll go over it. Okay, so let's go over our work. So in this first part, question number 2, we are asked to check conditions. So just like we've been doing all year, we're really checking, first of all, to make sure something was random. Now, in this case, we're looking for random sampling, and we did randomly sample our M&Ms, so we're good to go on that. Next, because we did random sampling, we need to check the 10% condition. We had 461 M&Ms total, and we need to make sure that's less than 10% of the population, which would be all M&Ms, which of course that is. So 461 is less than 1/10 of all M&Ms, and then we check that. And then next, though, we have this new condition, sort of. So we're checking large counts, which is something that we did already when we were doing significance tests for proportions. And this is similar. Remember yesterday when we were looking at finding expected values, we did n times p. So we're still looking at large counts and checking it the same way, n times p. But what's important here to notice is that the expected counts in this case need to all be greater than 5. This is different from the large counts that we do with proportions where they need to be greater than 10. So what I'd like you to do in the margin over here is I'm going to label all of these. These are our conditions that we're checking. So we've got random, 10%, but then also large counts, which I want to note here again. Large counts is when all expected values are greater than 5. Okay. Now what's important here is that you have to actually list out those expected values, or at least list what the lowest expected value is. Now we've already done that, so I just drew an arrow here to our expected values on the page. So that's fine. So if at some point on your paper you've already calculated your expected counts, all you need to do is make sure you note that somewhere. You don't need to list them all again. But if you don't have them listed on the paper, you do need to make sure you have them somewhere, meaning list them all or list at least the lowest one and note that you're only showing the lowest one. All right, then from there, we can calculate a p-value. So we started doing this yesterday, and I showed you how you can use table C for it. In order to use table C, you need to know your degrees of freedom, which is your number of categories minus 1. So in this case, our degrees of freedom are 5. And then our test statistic, we talked about already, is our chi-squared, which is 25.69. So I'm going to hop over to table C, and I'm looking here at row 5, and I'm going over until I find a chi-square test statistic close to 25. Well, that's actually off the page. So what that means is that our p-value is less than 0.05. So I've got that written here. That's just a reminder of how you find that. Okay, now we're going to make a conclusion just like we've been doing all year, where we are comparing our p-value to an alpha level. So because our p-value is less than 0.005, then that of course is less than 5% or 0.05. So we reject the null and we have convincing evidence that the claim distribution of M&M color is not true. And those are coming from our hypotheses from yesterday. All right, now this last question here, question number 5, they're asking us which M&M color was farthest from expected. So I could look back up here and just find the difference between all of these. So like from 55 brown to 59.93, that's 4.93 apart. And I could just look to see which ones are farthest. But actually what's important here, and I'm going to pop back to yesterday's notes, is when we're looking for the farthest away, you want to actually be looking for which is the largest chi-square contributor. And by that I mean when you're looking at all these values, which one is the greatest. And in this case, it's this 12.134, which is coming from blue. Now I point that out because when you look at the observed minus expected, blue is the greatest number between the two, or has the largest absolute value between this one and the next, which is the yellow one. However, that is not always the case. The furthest away in distance doesn't necessarily mean it's the greatest contributor. So you do want to check to make sure that the chi-square contributor, meaning each individual piece here, you're looking for the one that is the largest. So in this case, that is blue. And so I've got that written here, that blue is the farthest, and then what you want to include in your explanation is how far off it was, and then either above or below. So because this was a negative value when we looked at our table, that means it was less than expected. And in the margin here, what I'd like you to write then is that this is called a follow-up analysis. So if you're asked to do a significance test and then conduct a follow-up analysis, what we're looking for in your analysis is that you're telling us which value was the greatest contributor to the chi-square test, meaning that it had the largest observed minus expected squared over expected. Okay, so what I'd like you to do now is to go ahead and turn all of that information, so we've already done all the pieces that we need, but we need to turn it into a full significance test. And by that I mean we're going to put it into our 4-step process. So we're going to do this full state plan do conclude for our chi-square goodness of fit test. So I'd like you to take a few minutes and work through the rest of this page, pause the video, and when you're done, we'll go over the answers. All right, so let's go through this. So in this state portion, you'll notice here that we are listing our hypotheses and also our significance level, and they've told us to use an alpha of 0.05. Then in the plan portion, we are naming the procedure. So again, this is a chi-squared goodness of fit. You could also do it symbolically by just writing chi-squared GOF test. That is accepted as well, or pretty common practice. Then we're checking our conditions. We got random, 10%, and large counts. You'll notice on this one that I did list just my lowest expected count, which was the 59.93, and so I marked that all expected counts are greater than 5, but then also just showed my lowest. All right, so let's go ahead and talk about your picture. So it's possible your picture looks like mine here. So we're used to drawing normal curves. We put 0 in the middle when we're labeling our test statistics. So I've got 0 here and then my test statistic. But what I want you to do is think about what we said yesterday, that if we had a distribution that was very close to expected, then our chi-squared would actually be at 0. It actually is impossible to get a negative chi-squared value because remember, you're squaring all of your observed minus expected differences. So if you're going to square them all, they're always going to be positive. So chi-square is actually always positive. So if you have this picture, just go ahead and cross that out. And instead, how your picture should look, well, we talked about how the best chi-squared you can get is 0. So I'm going to start with a 0 here. And then it's actually going to be a right skewed distribution. So when you're drawing these, what you should do is you should label chi-squared. And then just like with a t-distribution, with a chi-squared distribution, we label degrees of freedom, which would be 5. And then my x-axis starts at 0, and then I'm going to go out and I'm going to label my chi-squared value on the x-axis, which in this case would be that 25.69. Now really here you're just sort of approximating, and actually how I just drew this is probably a much greater area than what I need, because remember it's going to be less than 0.0005. However, you don't have to be super picky on that. You just want to show like, okay, it's fairly far away from 0. All right, and then next I've got my specific formula. So that's chi-squared equals the sum of all of the observed minus expected squared over expected. When you're showing your work, you should show, I like to show the first two contributors that start at the beginning, and then just do a dot, 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 and then show the last one, and then your final chi-squared value. So that is our test statistic and the p-value. So in the do portion of your chi-squared test, we're looking for a picture, specific formula, all of your work, and then your answer essentially, so your test statistic and your p-value. And then I've just listed my conclusion again that we already wrote on the last page. So the last thing I want to talk about here is I want to think about, okay, what parts of the usual four-step process, so the ones we've been doing for, say, a one-sample t-test or a two-sample z-test for p1 minus p2, things like that. How is this four-step process different? So in other words, what parts are missing? Well, if you look back at the state portion, we have hypotheses and significance level, but we're missing a parameter and a statistic. So often we write, well, we always write our parameter in the state portion, but then also the statistic can go in there, so you have it written down. So we are missing that. We actually don't have a parameter or a statistic. And then we're also missing a general formula. We just go right to our specific formula here. So those are the parts that are different for a chi-squared significance test from, like, say, a z-test or a t-test. All right, so let's go on to the next page, and we're going to fill in the important ideas. So remember we said we had 3 learning targets, and the first of my learning targets was to check conditions. So first condition, we are checking the random condition. Next, we are checking the 10% condition since we had done random sampling. With this, I'm just going to mark, I like to use lowercase n for the sample is less than 1/10 of capital N for the population. And then the last part here is that we are checking large counts. That is our last condition. And this is that all expected counts are greater than 5. And then here you either need to, so I'm going to add below, you either need to list all counts or the lowest. And by that I mean if already on the page somewhere you've calculated all the expected counts, you can just draw an arrow to that. If you haven't done that on the page, then you're going to want to go ahead and just list the lowest one, like say if you did it in your calculator. And then our second learning target was about conducting a chi-squared goodness of fit test. So I'm going to put chi-squared GOF test. This means we're going to do our full 4-step process. So in the state portion, we have just our hypotheses and our alpha level. In the plan portion, we have the name, which is the chi-squared GOF, and then checking conditions. In the do portion, we have just our specific formula, which I'm going to put on here just so we have it. So chi-squared, the sum of observed minus expected squared over expected. So we have our specific formula and then also a picture, which I want to note again is a right skewed chi-squared and degrees of freedom. And then we need our work, which includes our test statistic and a p-value. Finish then, of course, with conclude. And then also, if significant, I'm going to put here, then you should do a follow-up. And for follow-up, then we're going to get into that in this last part. So for a follow-up analysis, what's important here is that you're identifying which category was the largest contributor to the chi-squared value. Or to the chi-squared test statistic. And what we mean by that is, of course, we're looking first to see which observed value was farthest from expected, but really we're talking about it proportionally. And by that I mean when we're doing a chi-square test statistic, we're calculating observed minus expected squared over expected. So what that means is, let's say you were expecting to have 100 of whatever your thing is. So you have 100 of them, but you actually got 99, so you're off from 1. You say, okay, that's not really a big deal, we're pretty close. Well, what if you were expecting 2 and then you only got 1? Well, then you've lost 50% of what you expected. So proportionally, that's going to be a greater value for your chi-square test statistic than if it were, say, 99 out of 100. So what we're looking for here, you want to first check to look for, okay, which value is the furthest from expected, but then you also want to check to make sure proportionally is that the furthest from expected, meaning you're looking to see is that the largest contributor to your chi-square test statistic. So go ahead and pause the video and then try this problem. And when you've got it all filled in, come on back and we'll go over the answer. I have given you a full 4-step template down here, so you can just sort of fill in the spaces as you go. All right, so let's go through the problem. So start with our hypotheses. Now, we talked yesterday about how when you're doing a goodness of fit test, you can say the claim distribution is true and the claim distribution is not true. And we could do that with this one. However, when I'm asked a question about if we have convincing evidence, what I like to do is I'll say, do these data provide convincing evidence that, and everything after the that is your alternative hypothesis. So I actually start by writing my alternative. The distribution of car color in Oro Valley differs from the North American distribution, and then my null is just the opposite. So the distribution is the same as the North American distribution. So you could rewrite those in your own words. I just prefer to rewrite them in the way the problem stated it. In the plan portion, we're checking our conditions and naming the procedure. So again, chi-squared goodness fit. Conditions, we've got random, 10%, and large counts. Now, this is an example of when you may not want to list out all of your expected values. So I can tell very easily from the problem which one is going to be the lowest, because this 2% right here, when I do n times p, I know that 2% is going to give me a lower expected value than any of these other proportions. So I just showed on here only the lowest count, which is 300 times that 2%, which is 6, which is greater than 5, and then so I just stated that all expected counts are greater than 5. Specific formula, so we just have our chi-squared test statistic formula. Picture, remember here you are doing a right skewed distribution, label it chi-squared, and then label with your degrees of freedom. There were 8 categories, so we have 7 degrees of freedom. And then I also labeled my chi-square statistic once I knew what it was. So that's 29.92, and so I just labeled it out here and made a really small area. I usually do that after the fact once I know what my test statistic and p-value are. For showing your work, because of spacing here, I only showed 2 of the components. So I've got the first one and the last, and then my chi-square test statistic. I often will do these in my calculator using lists. That's a nice way to be efficient. And then go again to table C. And again, we have a very small p-value here. It's less than 0.0005. So same conclusion as before, because that p-value is small. Let's fix this. So because that p-value is less than 0.05, we reject the null, and we have convincing evidence that the distribution in the Oro Valley differs from the North American distribution. So again, I'm just restating what the problem asked. They started by saying, do the data provide convincing evidence that? And so you need to actually answer, well, do they? Well, yes, they do provide convincing evidence. So I'm stating here that we have convincing evidence that the distribution differs from the North American distribution. And then next, because it was statistically significant, we want to provide a follow-up analysis. And so I'm looking here for which is the largest contributor to chi-squared, which was the other category. So I want to list that and then also say why it was different than expected. So for the other category, there were 18 more cars than we expected there to be. Okay, so that is everything you need for chi-squared goodness of fit test. Tomorrow in the next lesson, we'll be looking at a different type of chi-square test. There's actually 2 more to go, and then that will wrap us up for chi-squared. See you then.